with these basics, with these foundations, I think that this is the good moment to go to the digital twin concept. Do you remember where you were going, for the old people like me, do you remember where you were going to the school, high school? Well, in philosophy, in the subject of philosophy, we were instructed about the Plato, the Plato world, the Plato idea. Well, this is I like this similarity with the digital twin. The Plato concept is precisely the main, let me say, basic in order to create a real digital twin. So what does it mean? The Plato concept means the following thing. Do you remember this picture? We have sensors that they are highly specialized in a very specific task. Well, the thing is, when you are able to create the cyber reality, the virtual reality that is being covered by a physical thing, in this virtual world, and this is because why Plato is coming to the scene, in this virtual world, you can emulate things. For example, imagine that you are driving this autonomous car, and Mr. Tesla has the virtual thing of your car. In this virtual world that is in the cloud, there are AI models that they are running continuously, and they are emulating, calculating, simulating what could happen if this other car is breaking up, what happens if the traffic light will become red, whatever could happen around this device, but in the virtual thing. So this is why Plato is coming to the scene. In the digital twin concept, we are talking about a cyber reality that is emulating and controlling on real time what's happening in the real world, and using an orchestrator like AI, using this brain that is directing everything and this is trying to emulate what is happening and what could happen in the immediate future, we can have the digital twin concept. So digital twin is the combination of many smart industry technologies. IoT, of course, because we need this kind of direct connection or real-time connection with multiple sensors sending information around the device to the cloud. In the cloud, we have this Plato concept where we have the cyber reality, the cyber image of the thing, of the object, in this case, a car. And putting that in movement, we have a system that is able to react based on any kind of input. What happens if suddenly is a person crossing the street? What happens if suddenly the traffic light is switching off to red? These kind of things can be calculated in the cloud, and depending on which is the capacity and the edge, the IoT, you can have part of these decisions that also in the edge. So this is the concept of the digital twin. And this is not only considering your own device. The good thing is that the digital twin of this object that is made by multiple sensors connected between them through the cloud, not between them physically, connected to them by the cloud, they can have interaction with other digital twins. Okay, so if you have another autonomous car that is able to connect with both cars, they are creating digital twins for each of them, and each digital twin is connected between them. Okay, so this is the Plato concept. This is the AI as the orchestrator of everything, and the concept of the digital twin. I like a lot this example. Do you have Roomba at your house? That Roomba has a very powerful industrial Internet of Things inside their mechanism when they are working at house and they are cleaning the house. Do you know that Roomba has this Plato concept in a superior entity, because Roomba is establishing a map of your house in order to clean the house in a more optimal way. That so far until now it seems that it's clear and it's normal that a robot like this one with a lot of sensors is able to create a map of your house. For the reason at the beginning, the first days, the Roomba seems that it's a little bit drunk because it's moving around, well, interacting, choking with everything, with the chair, with the table, and so on. But after some days, the robot is able to go faster and more efficient through the floor. So it's this robot, thanks to IoT and also the small AI that they have in the edge, they are able to create this kind of internal maps. But do you know, or let me make you a question. Do you know what is the value, the added value of Roomba? Could you imagine which is the added value that Roomba can bring to the society? Maybe this is a curious question, no? Because my Roomba is for my house and I'm cleaning my house. So how I can insert in the society, no? Or how my Roomba can bring value to the business, which is the real business. Well, now I think that you are an expert on this kind of questions because we have seen that several times. We saw UPS. You remember that they were putting a lot of sensors in the tracks in order to optimize the routes. We saw this example in the thermostat Nest that was acquired by Google for $3.2 billion because Nest was selling the data of the temperatures and the climate in all the American houses, now in Europe also. We saw the example of Square. Roomba is following the same model. Do you know, have you visited IKEA? IKEA is a big furniture stores around the world. Mr. IKEA is purchasing data coming from Roomba. Did you know that? Why? What is the secret? What Mr. IKEA needs the data sent by Roomba? Well, Mr. IKEA is designing furniture, chairs, sofas, beds, based on the existing needs of the users. So at the beginning of the Mr. IKEA activity, this guy only designed furniture based on Scandinavian requirements. Nowadays, you can have a representative furniture in each country because Mr. IKEA is purchasing this data. So could you see again, what is the business value of Roomba? So when you are making business and when you are trying to do or to add value to your products and to your services, I think that this is a very good policy or practice to think about how we can bring value to our patients if we add more context, more metadata to the data. So this is a very good example about Roomba. But in terms of life science, I have a lot of examples doing the same thing that Roomba is doing. Imagine a bioreactor. We have this operation unit in upstream when you are making a vaccine or a bio drug in your systems. Well, the thing is that if you are able to mix product processes data, for example, it's not the same when you are producing this bioreaction in Denmark than in Brazil. If you add seasonality, if you add the utilities, the continuous changing and multivariability brought by raw material, you can have profiles, specific profiles of your batches. Because I don't know if you are involved in the research and development stages of the drug manufacturing, or maybe when you are doing clinical trials. I don't know if you are designing also the clinical trials, but I think that this is a very good way to understand the benefits of digital twins. When you are able to emulate to create a digital twin of an operational unit, a bioreaction, putting together the rest of sensors, like here in the Roomba, adding all those data that could potentially affect to your process, at the end, you will have, in the same way that Roomba is doing a map, a blueprint of a map about the roads and the roads that the paths that they are following, we can have also a path for each batch. So here we have a representation, a very easy representation of, let me say, in a PCA schema. PCA is principal component analysis. It's a classical multivariate approach in order to analyze multidimensional problems, numerical problems, if they follow a linear approach. Well, imagine that you are able to put all together. You can create a digital twin of your process with just a simple PCA, just making this principal component analysis where we can see in taking the most relevant variables that they are explanatory of the problem. You can paint, you can draw a batch, let me say, but not in the same dimensions that we are talking about. And this is how Roomba works. We are not talking about pH, temperature, speed of the agitator, and all those variables that we have inside the bioreactor. We're not talking about the external conditions, or we're not talking about product process. We're talking about new dimensions, mathematical dimensions, that they are combined, they are bringing more value, and they are removing all this noise that is not adding the specific value that we're looking for. Okay, so only with a PCA, you can create a digital twin of your process, because you have a fingerprint of the relevant variables that explain your problem. You have in the time, looking at the time, you can see the fingerprint of the golden batch, let me say, the optimal batch, the best one that you have identified in your history. You can have how much closer is your current batch, remember, current, real time, how much closer is your current batch regarding the optimal or the best one that you have identified in the history. But let's go again to the restrictions or the limitations that we have in humans. We cannot see that variable by variable. So you cannot see 100 variables that we have in a bioreactor. Actually, a bioreactor, usually they have 300 sensors. We cannot see the 300 parameters during 24 hours that my bioreaction is spending. We cannot see that. We need a digital twin that is able to manage all those dimensions in something understandable for the digital twin. And from a human perspective, we can condense all those variables, the 300 variables coming from the bioreactor, plus the 300 variables coming from the filling line, plus, we can condense all of them in just a few variables that they are explanatory of the phase that we are looking for. That, simple, that is a digital twin, but we need real time. Okay, I hope that helps a little bit. We will see that in detail later, but I need to make this introduction step by step, because we are creating these new ideas that we will see how they work. Well, remember, I was introduced before the Raspberry Pi. This is the Raspberry Pi, $35. We have all the pins that we can connect, the GPIOs that we can connect in order to connect anything that you can imagine, sensors of anything, very cheaper. But this board is not industrial. It's just to play at home, to make your experiments and so on. If you want to go to the industrial level, you have to add all the shield, all the industrial shield around the board. So it's not only physical shield. We were talking, remember, about also control systems, like what happens if I have a cut of internet connectivity. What happens if I have a electricity supply, a shortage of electricity. So we have to bring some battery or whatever. So that is happening. And this is the IoT Foundation with this kind of small board. And I'm sticking that this board just like an example, because we were starting the workshop introducing the democratization of technology. And that's true. With $35, we can purchase an amazing power computing in this board. Okay. Well, with a board with characteristics like that, we can control a full car in real time with all the systems already connected. And we can send the signals to the cloud in order to manage that in the cloud, in order to manage all the information and to make the right decision to send the conclusion to the device, and the device is able to be adaptive. Well, that seems nowadays seems so normal in the industry, and specifically in the pharma industry. This is not normal, but this is normal in the industry. We are seeing that in the streets. We are driving with autonomous cars used by Google, or autonomous taxis that they are driving in Silicon Valley without any problem. So that is a reality nowadays. But the pharma industry, specifically the pharma industry, is not already adopted because, well, several reasons that I would like to comment in tomorrow, because I think that it's important to understand why the pharma industry and medical services, they are not faster as other industries. I think that it's important to know that in order to put the remedy or the solution on that. And well, this is the slide that I shown yesterday, but the concept is the following. If you want to make the journey and you want to start applying this kind of Internet of Things and digital twins concept, remember that you can start from scratch using a scale like this one. You can think about critical components. You can think about assets, so combinations of these components. Later, you can go to operations, and finally to multi-system processes. So maybe a full upstream and downstream operation in order to track manufacturing. Okay, but this journey, it's important that after each step, you always think out how you can connect the different components between them. So please remember, don't create silos of data. This is so crucial if you want to move forward in this evolution. And well, this is an example that I will present later, how we can apply a digital twin in a bioreactor application. I don't know if you are used to work with bioreactors in your jobs. The bioreaction maybe is one of the most difficult drug manufacturing processes that we can imagine in our lives. When we talk about genetics using chemicals, it's really easy, because although we're talking about a lot of variables, they are analyzing these variables, analyzing the critical quality attributes of the materials, and putting in the right values the CPPs, the critical process parameters, and the setup parameters. You can have at the end the specific yield or the quality that you are looking for. But when we talk about bioreaction, we're talking about life inside a bioreactor that could interact with the rest of things in a very random way. So it's important to work, or well, it's important this example, because I think that the best candidate to create a digital twin in pharma is precisely a bioreactor, because we are working with lives. We are working with bacteria, with proteins, with yeast. So this kind of microbiological systems are really complex, and they can respond to external inputs in a different way and in an unexpected way. So from our experience in drug manufacturing, the best way to start is with something that is really difficult to manage in real life. A bioreactor is a very good way to start with a digital twin if you are making drug manufacturing. And I would like to have to bring here an example. This is the processes the sequence of operations needed in order to manufacture mRNAi products, let me say. As I mentioned, I think that on Monday, the mRNA strategy and the mRNA technology was created 10 years ago, practically at the same time than the fourth industrial revolution. And the first intended use for the mRNA medicine was cancer. But we didn't have any kind of approval from the FDA or from other health authorities. Well, the thing is that the preparation, the manufacturing of drugs based on mRNA strategy technology, this is not very difficult to do. So it's a very well-known technology that everyone can do, practically everyone. The problem is that we need a lot of phases. There is a very long chain of sequential steps where a single or a very small perturbation at the beginning can be amplified during the process, and at the end, all the process can be wrong, and we should throw to the trash the batch. Well, the mRNA is a very good candidate also to prepare a digital twin. And I'm very honored and I'm very proud to say that we're working with the Imperial College of London and also with the PDA. We will see that in the AI lecture, in order to create the digital twin of the full process of the mRNA vaccine. Could you imagine? So could you imagine to manage a complex problem like this one, where a dynamic recipe is being adaptive depending on the inputs and the outputs, what is happening inside each phase, taking the right decisions in every single moment in order to go at the end to the right quality of the product? You can do that using digital twins. Okay, so remember, I was talking about that in the Internet of Everything. Remember, the maximum level of complexity is processes, because there are a lot of assets in conjunction. We can do nowadays, with the technology that we have in the fourth industrial revolution, we can work with digital twins for full processes like the mRNA. There is an article, if you are interested. Here I'm writing an article, scientific paper, where a parallel initiative that is being taken by an independent team are working also in the same concept, in the digital twin for the mRNA vaccine. I hope that we can also publish very soon our conclusions. And well, in the health, we're talking about Internet of Things, but in medical Internet of Things. So we are talking about blood pressure, pacemakers, wearables that they are controlling our heart rate, and so on. We're talking about medical Internet of Things. And as you can imagine, a medical Internet of Things, they have similar requirements in terms of robustness, in terms of availability, in terms of security. We're talking about pacemakers installed, let me use the word installed in people in order to be monitored continuously. This is amazing, but this is a reality nowadays. So we're talking about this kind of technologies because we have sensors that they are fully dedicated, fully designed for a very specific topic. Well, do you remember that we are in this wave moving around from the centralized architecture to the distributed architecture? Nowadays, we are talking about distributed technologies, because we can, I don't know if you have listened to this concept, fog computing, that is so close to the blockchain concept. Well, fog computing means that you are talking about not only one cloud, you are talking about many clouds. And this is the reality. For example, Cuba is designing his own cloud. You are creating your own data center with your specific cloud. But imagine that you can collaborate with some clouds, some data centers in Slovenia. So you can bring power, joining both data centers, and you can create this fog computing system with more power than just the sum of both. Why? Because I'm sure that all your servers, all your computers, they are not running at 100% of the capacity that they need or they can offer. It depends on demand. This is even more when we have difference of time zones. So that happens even more. So you can create a fog node, you can create a fog computation with more powerful when we have different time zones, and you can take the power that is not consumed in one time zone by the other one that is doing that in the morning. Okay, so the fog computing is a concept that is increasing every day. And even more, the fog computing can be used also by cloud computing using a bigger network, for example, using providers, cloud providers. So this is some challenges regarding fog computing, which is the incentivation that we can bring to clients. When I say client, I'm talking, for example, about research centers, supercomputer centers, hospitals that they have their data centers that they would like to share data and power computing with other hospitals and so on. So this kind of oscillation about the requirements based on different time zones is a classical way to take benefits from fog computing processes. But I think that if you have time and you're interested in that, please take a look at this slide, because there are different challenges nowadays based on that. Imagine that you were working with different fog computing centers where all of them, they are located in the same country. So that could not be beneficial. That could be a problem when all of them, they are running at the same time because they have the same requirements of computing consumption. And with that, we arrived to the blockchain concept. And I think that here in Cuba and in Slovenia, you are really experts. So I will try to don't go deeply, but remember that blockchain is for something more than just Bitcoins. The foundation of this blockchain is decentralized and distributed system. So you can have donors, you can have volunteers that they are running with their personal computers, making, establishing the links between the chains, that they are defining something. For example, the audit trace, the trace and the track, trace and track of distribution process. For example, from the laboratory, the warehouse of the laboratory, when the drug is leaving to the pharmacist, and you want to ensure the traceability and the track and trace of the process, where the drug has been stopped, when the drug has been delivered, the drug to the pharmacy, and so on. If you want to keep this traceability in a non-violated way, in a more secure way, you need a lot of this distribution of computers, decentralized computing systems, that they are creating this blockchain. But we have some problems with that. This is the basics that I'm not going in detail because you are an expert on that, but the essence is that you have different seeds, you have different threads, and if you destroy some of them, some of these chains, the full chain can be created again, because every single step contains information of the previous one and the next one and the siblings. So you have information in the parents, the children, the siblings, so everything connected. There is an algorithm that can reconstruct, rebuild in case of necessity if some of these blocks is disappearing. The main problem nowadays, the huge challenge regarding blockchain, is the energy cost. So nowadays, one of the major sources of consumption of electricity and contamination around the globe is computing. So huge data centers, people that is working all the full day with their computers, like you and me probably, we are contaminating a lot. And there is a new trend that is trying to investigate how to save energy with less effort of energy. And we have a lot of IoT possibilities regarding blockchain. So imagine that all the things around your drug distribution, if you want to keep traceability, I think that is the best example and the best use of blockchain. If you want to keep consistency around everything that is linked in a chain, you can link them using IoT in order to send this block, this small piece of message, this one. Each block is sent by a computer, and each part of the sequence. For example, this is the drug medicine leaving the warehouse, and we arrive at the end to the pharmacy. So every single step could be informed by an IoT system and can be processed by several computers at the same time that they are creating this fog distribution. And this is how we are making smarter the edge. So when you put AI in the edge and not only in the cloud, this is important because you are facilitating, you are providing more power to the edge. So we are creating the content of the smart edge. Okay. And maybe, and this is how we can smell maybe the new stage of the wave. Remember at the beginning that we are now in the decentralized part of the wave. So in the next year, we will see how the centralized wave comes again. Maybe that could happen because we're putting more intelligence in the edge through blockchain, through AI, through this kind of fog computing. Okay, and just very quickly, quantum computing, I think seriously, I think that this is the future of the new evolution of the centralized architecture in the wave. Why? Because with quantum computing, we are multiplying by a factor or maybe two factors. So it's a growth, an exponential growth about the power computing with less size of chips. And this is so amazing. So here you have several comments, but let me explain you very briefly how that works. Maybe, I don't know if we have physics in the audience. I'm physics, and this is maybe my, I'm totally biased, but let me explain you very briefly how it works. In classical computing, we have bits. A bit is 1 or 0. So we have something that we can write with, for example, a letter, an A, a B, a C can be written by 8 bits. Okay. Well, the thing is, because we have an accent, we have to say if they are lowercase or uppercase and so on. Well, with 8 bits, you can define a letter. In quantum computing, we have the 0 and the 1 bit, because this is the classical bits, but we have a distribution in the middle that together can have 1 0 or 1. But there are many states in the middle that can bring a specific state different than 0 or 1. This is what doesn't mean qubit. A qubit is the minimum amount of information in quantum computing containing the same, let me say, amount of information that one classical bit could have. The difference is that in the classical computing, we have the ability to combine binary sequence of characters, zeros and ones. In quantum computing, for the same cost, we have thousands, millions of possibilities. Could you imagine how much information we can store in this sphere that in classic computing, we have only 2 different states? Well, this is why quantum computing can bring a lot of value. I don't know if you have made a quantum subject, but this is an example about how we can transform a probability of a state between 2 bits, between 0 and 1. Well, nowadays we have examples about companies that, for example, Volkswagen. It's unbelievable, but Volkswagen is working with quantum computing. Also Honeywell. Honeywell is a company that I'm collaborating with precisely in this kind of project. They are taking advantage of quantum computing when we need brute force. When we need, nowadays, quantum computing is practically totally focused in working with brute force, when we don't have power computing enough in the classical one to make iterations, we go to quantum computing. And you cannot imagine how much fast they are. So for example, for meteorological conditions, for satellite controls, when you need brute force, quantum computing is very, very good.